Hello, let's do the electronic configuration of elements. So you'll be learning something about quantum numbers, some rules by which the electronic configurations are written, and the examples also. A few examples we will take. So you know electrons are distributed around the nucleus as an orbital, and the distribution of electron density can be described using quantum numbers. We have 4 quantum numbers, starting with n, called as the principal quantum number, and this tells the position of an electron. Then we have another quantum number L, which is called as the angular quantum number, which tells us the shape of the electron. The next one is the magnetic quantum number, ML, and it tells us the orientation of an electron. NLM, as I said, describes the position, shape and orientation. We have MS, the spin quantum number, which tells about the spin of an electron. So using these, we should be able to write the electronic configuration of an element. And how do we go about it? Let's take up the values n can take. N can take values of 1, 2, etc. And L can take a value 1 less than L. And ML takes a value of -1 to +n. And L, as I said, it takes a value 1 less than n. Then we have a spin quantum number which has only 2. It can be either +½ or -½ I'll just add one more column to it called as the number of electrons, which we will know in each level how many electrons we can have. The principal quantum number 1 will give me an angular quantum number of 0, and which is given the symbol S. The corresponding magnetic quantum number is going to be again just 0. And then we have the spin is going to be it's going to be the same. We have two electrons we can have, one with the positive half and the other one is a negative half. So this gives me, for the first level, n equals 1, I can have 2 electrons. So when I take n equals 2, as n can take a value 1 less than n, I'll have 2 values of L, 0 and 1, giving me an S and a P level. And this gives me more magnetic quantum numbers, giving me the total number of electrons, 2 from S and 6 from P, as 8. So the level 2, n equals 2, will have total of 8 electrons. Then comes n equals 3. This will introduce one more angular quantum number called as D, and giving me a total of 2 plus 6 plus 10 electrons equal to 18. And n equals 4 introduces F, and this, if you calculate it, will give you a total of 2 plus 6 plus 10 plus 14, giving me total 32 electrons in level 4. So let's just revise. What did you learn? When n equals 1, I can have 2 electrons in that level. N equals 2, I can have 8 electrons. N equals 3 will have a total of 18 electrons, and n equals 4 has a total of 32 electrons. So I need a way of representation of these which will tell me what is the principal quantum number, what is the angular quantum number, and how many electrons are there. And the way we write that is 1s2. 1s2 means 1 is the principal quantum number, s means that is the angular quantum number which corresponds to L equals 0, and that level can have 2 electrons. So do anything, we have certain rules. So let's see what are the rules which govern the electronic configuration. The first rule is called as the alpha principle. This says that level with n equals to level, which is the lowest energy level, will get filled first. So we start with the lower energy level 1s, then we go to 2s, then we go to 2p, and so on till we reach the higher energy level. Then we have the Pauli's exclusion principle, which says that no two electrons will have all the four quantum numbers same. NLM can be different, but MS has to be different. We have another one called as Hund's rule, which says that we have to fill up the empty orbitals first, then pairing has to be done later. But you will be actually using Hund's rule in the next presentation only. So this time I'll be just using Haber principle and Pauli's exclusion principle. Let me take the examples as written on the board, oxygen to calcium, and try to write the electronic configuration of each one of them. The lower number is the number of electrons, is the number of protons an element has, that should be equal to the number of electrons, and therefore oxygen with 8 electrons, let me put 2 electrons in the first level, that is 1s2. The next one is 2s, which can also take 2 more electrons. So I'm done with 4 electrons. Now I have to accommodate 4 more. I'll put it in the P. So 1s2, 2s2, 2p4 is the electronic configuration of oxygen. So now we'll go to neon. Neon has how many electrons? 10. Therefore, if I add just 2 more to the 2p, I'll get the electronic configuration. Similarly, sodium. Since we have done with the 2p6, we have to introduce the next level, that is the 3. So I put in 1 electron in the 3s1. Then comes aluminum. I put 3 electron, 2 in the S level and 1 in the P. With chlorine, 17 electron will have this electronic configuration. But don't you think this is a pretty lengthy process? If the number of electrons become, instead of 17, if it is 47, imagine how long you have to keep writing. Is there a simpler way of doing it? Yes, there are 2 ways. There are 2 simpler ways of doing it. One is using a periodic table, the other one is using the inert gas configuration. This, we will use the inert gas configuration. So look at neon and the sodium. Don't you think this part is same? So why do you have to keep repeating it? Can I write the electronic configuration like this with neon in bold brackets? With just the outer electronic configuration of sodium is written. And same case with aluminum also. This part is same. Therefore, I can write electronic configuration of neon 3s2, 3p1. Chlorine also follows the same way with electronic configuration of neon 3s2, 3p5. So this gives me an easier way of writing. I have to just look at the inert gas before the element and write that and write down whatever is left in rest of the orbitals. So can I apply that to calcium? So argon is the inert gas before calcium and has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Calcium with 2 more electrons will have this electronic configuration. Since this part and this part is same, in case of calcium, the electronic configuration of calcium can be changed to electronic configuration of argon and 4s2. Or in other words, any electronic configuration can be written using the inert gases. In this example, I've taken only elements up to calcium. It is easy to write the electronic configuration of elements till you reach calcium. 1 to 20 it is easy. Even in calcium, if you have noticed, 3D is not there. I have filled in 4S. So something is there with calcium. Or this needs more explanation. Or what do I do for elements after calcium?